This is sort of the section of Cryosphere Day where we are moving a little bit into the policy world. Most of the focus today is on cryosphere science, about the impact of climate change, about what we're looking for in the future, but there's also in terms of adaptation and in terms of mitigation. We have this session right now coming with the On Thin Ice report, and also very, very interesting outcomes of the High Summit Conference of the EV-K2 CNR committee. So I'll turn it over to Sandro Fuzzi, and then we'll bring the On Thin Ice people up. Thanks.
Okay, thank you. Usually the first talk in the afternoon is the most difficult one, with people having heat from the interior to dissipate. So my talk will not be a scientific one, but it will concentrate on some issues and some recommendation which came out of the iSummit conference that was held a few weeks ago in Lecco, Italy. I think there is. Okay, so the Rio Plus 20 conference last year identified mountains as essential ecosystem to be preserved, because several reasons. The most important ones are that mountains are a source of fresh water for a large portion of the world population. Mountains are very fragile ecosystems which are much more vulnerable than other areas to climate change, and also mountains are home to communities which are often marginalized, that have developed sustainable use of the resources. Then a couple of months ago, the summary for policymakers of AR5 came out, and the two overarching statements to me are that warming of the climate system is unequivocal, and that the human influence on the climate system is clear. So since 1950, substantial changes have occurred within the climate system, and some of these changes are unprecedented over decades, and in some cases hundreds of years to millennia. And as we all know, this has caused increase in temperature, the increase of the heat content of the ocean, the increase of the temperature of the ocean itself. But for the issue that we are discussing today, we have heard from Georg Kaser this morning and from others that the glacier volume are generally decreasing, that the snow cover area is decreasing, and also the sea ice areas. So in this context, we organized the international conference in iSummit in Lecco last month, which has gathered representatives of the international organizations dealing with mountains, mountain stakeholders, and scientists from a broad range of disciplines to discuss the scientific and socioeconomic status of knowledge on mountain ecosystem in connection with climate change, but also to issue recommendation to policymakers on the action needed to mitigate the risk induced by climate change, and to suggest also adaptation strategies. You'll find outside some leaflets which report the essential outcomes of this conference. I will try to just to highlight some of the most important points here. There is no way that I can go in depth into that in the interest of time. The first point concerns the observations in mountain areas, which we know are very sparse, very difficult to obtain, and if we want to investigate a problem, of course, we need the data. So mountains are unique platforms to monitor the changes of the air composition and of the parameters linked to climate, and usually mountains represent wide geographic areas, as in the case of the Global Atmospheric Watch system of WMO, which out of 29 global stations includes 9 mountain stations. The 2 stations in red, I highlighted in red, are the ones which are managed by the organization I belong to. So Monte Cimone in Italy and the Pyramid in the Himalayas. Concerning glaciers, we have heard already several times this morning that overall glaciers have continued to shrink, although there are also cases which show the opposite, but on a budget level they are losing mass, and the current glacier extent are out of balance with climate condition, indicating that the glacier will continue to shrink even if we would stop the CO2 emissions today. So we know that glacial meltwater feeds river during the warm and dry season, and there is a need of a more accurate knowledge of the different elements of the cryospheric system in mountains and the changes that it is undergoing. Concerning water, we know that the seasonal shifts of the hydrological cycle will take place in the near future in mountain areas worldwide, and this will have implication in all fields of our life: agriculture, food security, drinking water, hydropower, and it's also can also be responsible for hydrogeological hazards. So for these high altitude mountain research dealing with the hydrological cycle and its changes should be strengthened, and monitoring should be improved. on the effect of climate change with a particular focus on the precipitation cycle. Concerning mountain ecosystem, as I said, we lack information. So there are still many uncertainties, and their response to climate change is still not very well constrained. And at the same time, the mountain ecosystem can provide also services for the people who live there. So in this way, it's essential to improve the communication between the science community and the local stakeholders, local population, in such a way that the further research is more user-driven, which means, for example, that we should improve also the dissemination and the capacity building on the importance of conservations of this fragile ecosystem, and also from economic standpoint, which are the so-called ecosystem services. The last issue that was discussed concerned the socio-economic impacts. It's particularly difficult for the natural scientists to have an interface with the social scientists, and that's something that was achieved in this iSummit meeting, because the emissions that we are supposed to reduce are dependent on socio-economic factors, which on their way depend on the political will. So what was recognized in the conference is that some important assets are not taken into account in the evaluation of the GDP. For example, the natural and human capitals, and there were presentations dealing with economic tools which can identify the value of the economic contribution of mountain ecosystems, such as the environmental services, forests, and sustainable agriculture. And the economists present there stressed the need of study and then apply some economic tools that you see listed here: environmental taxation, payment for environmental services, and so on. So these were the main issues and the main recommendation coming out of this iSummit conference. As I said, outside you can find a more detailed description of this point. So I close here, and I thank you for your attention.
And we'll have questions for the entire policy section, in a sense, all at once at the very end. So I think it's easier if anyone's up here, so if I could ask Karen Kemper, Elisabetta, and Zig to come to the podium, please. And the On Thin Ice report is, yeah, please come to the podium, yeah. The On Thin Ice report is, I would say, a wonderful example of a science policy interface. So it is, I think, as most of you know, and there are copies outside. It has both an executive summary, which has been translated into several languages, actually, and will be made widely available then to COP19 delegates at the ICCI booth over the next week. Please have a seat. Yes. And I'm going to be passing out right now also some very nice sticks that were produced by the World Bank in addition to a lovely production by the World Bank. Karen, you might want to hold this up again. Yes. Oh, Sandra, you don't need to sit up here if you don't want to. Yeah. I'll be passing those out as they speak because they have not only the On Thin Ice report in both versions, but the Banks Turn Down the Heat report, the methane financing group, and perhaps even some other studies that are included. So, yeah.
Okay. Well, good afternoon, everyone. I'm very glad that Sandro did the right after lunch talk, so I get the second right after lunch talk, and we all know that's a bit of a challenge, but we also think that we have a report here that really would wake us all up, as does the entire topic. And it's really my great pleasure to be here today and to talk about this brand new report. And I'll hold it up one more time so you can get a copy when you get out. But also, really, before talking about the report, I would like to thank once more the ICCI, especially Pam and Svante, for convening some of the really best scientists in the world to work on this report. And it's the organizations that have been involved in this, and many of you are from these organizations, and obviously here on the panel also are NASA, JRC, Istanbul Technical University, University of Reading, EASA, SEI, UC Berkeley, and the US EPA. So it's been a great collaborative effort, and of course we are very proud to be associated with it. Because we can very much rely on the underlying science, and for us it has very clear business implications. It's because you will wonder, so why is the World Bank really so interested in the cryosphere? Why the World Bank? Why are they sitting here? Well, for us it's really a very important issue because as a development organization, we look at the developmental effects of this, and we just heard some of Sandro's presentation on, for instance, on the effects on mountain ecosystems, what that can mean with all the impacts on mountains and the cryosphere in general. And in the bank, at our annual meetings just a couple months ago, we endorsed a strategy for the World Bank that aims to eradicate extreme poverty and to boost shared prosperity by 2030. So for us to get there, obviously climate change and its impacts are going to be a major obstacle. And if we don't confront climate change, then we won't end poverty. So for us, the two topics are intrinsically linked, and that is where our interest comes from. From our perspective, aggressive action to reduce short-lived climate pollutants like methane and black carbon is very important because it buys our clients, the developing countries, and especially the poorest and the most vulnerable ones, critical time, including in order to adapt. But then equally important, and I'll talk a bit about it, and then Elisabetta and Sie in much more detail, equally important, one can also reap very huge health, agriculture, and other development benefits by the same things that one would be doing while trying to reduce methane and black carbon emissions. So you have very, very strong co-benefits on the developmental side, and that is what the report focuses on a lot. It makes a very strong case for action and for action now. So the report explores changes that are being observed in five major cryosphere regions: the Andes, Antarctica, the Arctic, East African highlands, and the Himalayas. You have heard already this morning, and many of you are working on these issues anyway, about the issues of sea level rise that are associated with it, the issue of water resources being threatened, and so on. But for us, that really translates into people. So in terms of, for instance, the rise in sea level, that would affect like 100 million people globally. The water resources, for instance, the Indian subcontinent alone, that so heavily depends on the water towers that the Himalayas constitute, it would affect 1.5 billion people. And that's the 1.5 billion people of today, and not the perhaps 2 billion people of tomorrow. So it has major, major impacts on people and their livelihoods. So if we act fast and we cut back black carbon and methane, we can slow the rate of warming. You all have been talking about that today. I mean, that is why many of you are so interested in this. But for us, it also means we can save millions of lives, and we can improve the health of many more. We looked in this report at 14 measures that one could take. They were initially proposed in a 2011 scientific assessment by UNEP and the WMP. And those 14 measures, actually, that you will hear more about from Elisabetta, those could get that job done. So it's not an impossibility, and we have the technology of doing it today, and we can see from the report that there is a social and economic case today to do these things, and you don't need to only look at the climate benefits, but you also get local benefits that completely warrant to do this. The 14 measures together could slow warming in the Arctic by more than a full degree by 2050. And that in turn would result in up to 40% reduction in loss of summer ice and 25% reduction in loss of springtime snow cover compared to the business as usual scenario. So this is actually quite dramatic that one would be able to do this. It's not something where one has to wait for the future and maybe then think about what one would be doing. So scaling up just 4 cook stove solutions, for instance, which are covered in the report, could save 1 million human lives annually while delivering climate benefits to, for instance, the Himalayas and the communities that depend on the Himalayas and the ecosystem services that they provide in South Asia. Or improved wood and coal heating could save another 230,000 lives, while a 50% drop in open field and forest burning could result in 190,000 fewer deaths every year. And those benefits would then be seen mainly in Europe and Central Asia, for instance. Another example is reductions in emissions from diesel transport and equipment could result in more than 16 million tons of additional yield in crops such as rice, soy, and wheat. Some of you may have been following the agriculture discussion here and the food security discussions. So obviously that is quite an important result if one could achieve it. And one would also be able to avert premature deaths of around 340,000 people. So these are very, very strong figures that this report has been able to show. So that is one of the reasons why the World Bank has the strategic intent to move from what we call SLCP relevant activities to SLCP reducing activities, meaning that we will look at how we can actually help reduce emissions when we get requests for certain types of investments. We do that already. That's the good news in a chunk of our portfolio. So we have investments already now with, for instance, Mexico, Colombia, Nigeria in bus and rail-based transport systems that substitute for diesel in trucks on the roads. Solid waste collection and disposal methods. We've financed such things, for instance, in Rio de Janeiro and in Amman. We are working in the context of the Global Cook Stove Alliance to help improve cook stoves. We did hear yesterday how difficult that is, and we know that. But the fact is that we would do that anyway for the health benefits. The key issue here is that we now have a linkage also to climate change, but for health benefits we know that especially for women and children it's really important to work with cook stoves, especially indoor obviously. We also work with brick kilns to make them more efficient, for instance in Bangladesh. And one big area that I think there still needs to be collective activity and research around it to a higher extent than what we've seen so far is on rice irrigation, where we know that there's a lot of methane emissions, but how does one really manage to reduce it? And I think we are not quite there yet on the methodology side, but at least we think one should try and one should focus on that. So we recognize that none of these activities will be easy, and there are real barriers to implementation, both on the cost side, on the behavior side, technology and sustainability, but a lot of things are already happening, and as I just mentioned, there are a number of examples. So we recognize that we need to do more. And through our presence on the ground in many of the partner countries, the bank is very well positioned to work on a country-driven approach to reduce SLCPs and maximize these co-benefits of the interventions. We are also looking, of course, at financing solutions. One needs a lot of finance for a number of these things. We were encouraged by the Climate and Clean Air Coalition to design a facility to finance methane reduction, and we are in the process of doing that. We are actually ready to go. That facility would help would help top off the 1,200 projects that are currently stranded, that were done already and prepared for the CDM mechanism, and then the carbon price crashed, and now it's not worth it anymore. So this would actually help bring about such projects that we know already. They would address SLCPs now in the next few years, and certainly before 2020, and we really hope that we can get that together, including with a range of donors. So to conclude, the report is another reminder that the benefits of strong and early action on climate change, an action that follows clean and low carbon pathways and avoids locking in unsustainable growth strategies, that it far outweighs the costs. It also shows that this can be part of a work agenda pre-2020. We do not need to wait until post-2020. And there's really a lot that we all can do together. Now we know this is not sort of the silver bullet solution to global warming, and this, of course, on the side of the World Bank goes completely hand in hand with reductions in CO2 emissions as we look at low carbon pathways. But we also see it as something where we can get short-term gains fast, and we would want to work for that very much. So with that, I thank you for the attention.
Thank you, and hopefully, and we know that your schedule is very, very busy, but hopefully you'll be able to stay for a few questions at the end of this. Okay, wonderful. And so we'll turn now to the report itself, and I know one of the first questions one always gets with the UNEP WMO assessment, as well as with this report, is what in the world are these measures exactly? And so Zig Clement of IASA is going to address that, and then Elisabetta Vignati from JRC will speak to the modeling results in greater detail. So
where do I find the presentation?
if you've loaded it, it should be on there. Yeah, there you are, number 10. And while that's loading, I would say also that one of the things that's so gratifying with some of the work at the bank right now is the methane financing facility, which we've been working on, recommending to get started with the Blue Ribbon Panel since 2009, and it's wonderful, although it's taken 4 years to see it finally getting so close to realization.
Thank you, Pam. Good afternoon. Thank you very much, World Bank and ICCI, for inviting me here and giving you a chance, or giving myself a chance, to give the only talk that doesn't talk about cryosphere on this day of cryosphere. So that will be something that is different about this presentation. And also, most of the stuff I will present is not available in the report that you were advertised now. There may be 2 slides that very directly point to information you find in it. I'll make a little step in time and talk about the origins of the measures that were just mentioned and linked to the UNEP report, and talk a bit about how we came to the idea of putting these measures forward, and then say a few words about how important they might be. This is the approach that was used in both studies, or in several studies, actually, in 2 studies of UNEP that are shown in here, and also in the thin ice study. So what we started with, we looked into a baseline projection. This baseline projection relies on International Energy Agency energy projections at most, and then there's some other information on agriculture and other sources. To put it in perspective of RCP studies that were RCP concentration pathways that were mentioned already today, this projection is consistent with RCP 6 watts per square meter at the end of the century. But in terms of air pollutants, aerosols, and gases, it's a bit different. It's on a high end compared to the RCPs. And it extends only until 2035 that was used in this study. So we constructed a baseline scenario for a number of air pollutants, and then looked into radiative forcing of the sectors. And the important part in that was a ranking of mitigation measures. So the question that we asked ourselves was, what can we do to mitigate air pollutants that would also bring some benefits to climate change? Or the way we formulated the question was that would reduce radiative forcing. And I will illustrate that on one of the other slides. We used the Gaines model that I will also explain at least briefly, and consider a number of pollutants in interactions of these pollutants, interactions using simply global warming potentials in order to put them sort of on the same scale, and filter out measures. The question that we asked ourselves again was, can we construct a case for very few measures? Very often policies end up with discussing endlessly complicated legislation that addresses a number of sources and hundreds of measures. We tried to put it together into small amount of measures or set of measures, and still managed to address a large proportion of total emissions. And I think we were fairly successful. Eventually, what you will hear later from Elisabetta is the 5th step here, the climate impacts and co-benefits of these selected measures. So this was the past, 2-3 years ago, the UNEP reports. What is different on Thin Ice report, it's not only that we did revise a little bit of information about the measures and information about them, but also added a couple of measures or eliminated some of them. The report used 3 rather than 2 climate models and analyzed single black carbon measures. So this is a big difference, because instead of looking at the impact of all the package of methane measures and black carbon measures, like it was done in the UNEP reports. It looked here specifically measure by measure and focused on even more on regional aspects, specifically cryosphere. There's a couple of different aspects that I might mention if I remember during the presentation. So this is the framework that was basically repeated with some of the updates, or very significant updates actually, in this On Thin Ice report. Let me start with at least one chart that shows a map. All the others are much less exciting than most that I've seen today during the day. This is showing emissions of black carbon in 2005. And what happens when we move forward towards 2030, according to this baseline, is maybe not much the way you saw it now. Let's focus on United States and Europe. If you just look at United States and Europe, you see a sort of yellowish, I don't see even this red thingy in here, yellowish and reddish. This is Asia. If we just focus on these two and I flip to 2030, you see they improved dramatically. While I go back again, while Asia and Africa remains pretty red. There's some redistribution and maybe increase. Emissions overall stay about the same level, about 5 million tons from anthropogenic sources. This map does not include emissions from forest fires and savanna burning, so it's only anthropogenic sources. And what is important here is that this change that we project until 2030 means that the mitigation opportunities between Northern Hemisphere and Asia and Africa are very different, and we have to capture that in our analysis. Okay, let's move on to the tool that was used to produce both these emissions as well as rank and identify and rank the measures. The GAINS model came out actually from the RAINS model that looked into air pollution and looked into sulfur dioxide and then nitrogen oxides and all of these compounds that are listed here. And this typically air pollution linked effects, health effects, as well as ecosystem impacts. Later on, it evolved to include Kyoto greenhouse gases and long-term climate impacts. Eventually, in order to perform this analysis, we have added specifically black carbon and organic carbon within particulate matter and looked into near-term forcing and black carbon deposition. The plus and minus on this chart indicates warming and cooling from the gases, long-term gases, and here in this case aerosols and gases. So using this framework that contains information about emissions, distribution among many sources, something in the range of 2,000 specific technologies for 190 regions across the world. We've tried to rank the measures and looked into a question, could we find the win-win air quality measures with co-benefits on climate change? The co-benefits in this case identified through the reduced forcing calculated with global warming potentials. So we're looking into some of this, some of the warming, black carbon, ozone precursors, cooling, sulfate, and organic carbon, little effects from the others. These substances are co-emitted from the same sources in principle. Most of the sources that produce CO2 produce also all of these pollutants. So there's always a balance. If you introduce any reduction measure, you cannot reduce only one of them, but you will reduce a lot of them. And they will be reduced depending on the measure you choose. The impact will be different from measure to measure. So what we are doing, we are trying to quantify that. This is an example illustrating how the selection procedure works. So it's a very simple approach and a very simple way of eliminating measures that go in the wrong way. What we see here is emissions for one particular source, wood cook stoves in India, I think. And these are absolute emissions shown for 3 types of stoves. If you would take all wood that is burned in cooking stoves, in traditional cooking stoves, this is the black carbon and organic carbon emissions, sort of a proxy for particulate matter, although it's not total particulate matter. but let's look at those substances, because typically we talk about black carbon, organic carbon as the warming and cooling and counteracting each other. So there's been very often arguments brought that many of the measures put forward will cancel sort of itself out because of the organic carbon reduction that is removing the cooling particles from the atmosphere. What you see in here is that indeed, on the emission metrics, if you move from a traditional to so-called rocket stove, this kind of stove has been promoted by many of the programs, like the USAID or a lot of other organizations that promoted stoves that improve dramatically or reduce dramatically emissions of CO and particulate matter. And you see here there's a huge impact in total emissions. But if you look at the black component, there doesn't seem to be a lot of change in emissions of black carbon. That's the black one. While the fan stove, which is the fan-assisted stove when you pump extra oxygen, air, reduces drastically emissions of both compounds. Certainly the winner. But there's a lot of this kind of stoves out there, and the second part of that chart is trying to put that in the perspective of what does it mean when using global warming potential, using only black carbon and organic carbon. So the red dot in here indicates the direction into which the combined forcing moves. Moving up is bad, moving down is good, is reducing forcing. So what happens when you remove a lot of OC in this kind of stove is that the forcing from cooling OC is coming down dramatically, much more dramatically than the forcing, positive forcing from black carbon. So overall, it looks like it's going in the wrong direction. So a much preferred option from the climate perspective, it still saves lives. There's no question about that, and you will hear about that from Elisabetta. But the question is, okay, we have to move in here. Maybe that's not affordable. Maybe that's not possible. We have to look into some of the options in between. It's important to understand it. But there's one more thing that we should not forget. That's the last part of that slide, that eventually the analysis should include all the other gases. And this is what is shown in here. If, for this particular example, we would include all of the other gases, and SO2 is also appearing in here as a tiny little blob on the bottom, but all of the greenhouse gases here, and CO and non-methane VOC, reduced drastically actually for this rocket stove, make the picture look quite different, or a little bit different at least. This is just to highlight the way that the analysis was done for each of the measures, and looking into picking those that resulted eventually in this kind of move, and grouping them into larger categories so we can grasp them easy. What we come up with is this list of measures that was mentioned. We could discuss long about the number of these measures, depends how they are presented. You will find also in this report that sometimes it's 14, UNEP report had 16, but that's not so important. There's few of them. It's the same measures for methane that were used in all of the three reports, both UNEP report and this one, so there's no difference for those. And there's black carbon measures, and there are some differences in terms of measures that were picked up specifically for this report. For example, you don't see here brick kilns that were in the original report, but you see reduction of flaring emissions that were not included in the UNEP report. You see two extra measures here that look into biomass burning and target specifically total biomass burning globally or reduction in particular area, strong reduction. So these are new elements that are added specifically for this study. What is important here is that these measures, first of all, are relatively few. Of course, these are rather categories of measures. When we talk about diesel particulate filters, of course, we have heavy-duty trucks and cars and tractors and lifters and various machinery out there. Each of them is a specific measure that has its own cost and slightly different reduction efficiencies. But in principle, it's the same category, the same type of technology. So this is grouping these technologies that could be also regulated or discussed in terms of mitigation, future mitigation, in the same forum, in the same group, having the same people around the table, understanding what we are talking about. And the other thing that is very important is that these measures center around very few sectors. So we don't have a large number of industries or other fora that we need to address when we talk about these measures. We have transportation here. These all these measures, from improved cooking stoves to improved heating stoves, addressing one sector, residential combustion. We talk about industry here, oil industry, that is also reflected strongly in the methane measures. There's gas and oil industry reflected in here. Then we have coal industry, large-scale industry again, in methane measures. This is open biomass. That is a very difficult measure actually to do, but there is some practice in certain areas. Again, very different actually from community that discusses transportation. They could be tackled independently and have their own time frames. I will come back to that. And there's also agriculture that is coming out here, and waste that was already mentioned. Now, if we, this is a slide that actually appears in the report. You find it in the annex, in the On Thin Ice report. This shows, for the example of black carbon measures, specifically impact for each of the compound in terms of reduction. Compared to the baseline in 2030, this is reduction measure by measure, and 2 cook stove measures. These are the most prominent measures that appear in here. And you see reduction for many of the pollutants. The reductions are very significant, running into 40–50%. And if you take all of the measures, they are much more ambitious. What is interesting here is to put it in the perspective, what is possible. The black lines, or the black whatever dots here, or parts of lines, they indicate the maximum potential, technical potential, that has been identified in the Gaines model. So this is how far you could go if you would implement all of the measures that are included in the model at this stage. Now, if I add up, of course you cannot add up these two because they are either or they would apply to different regions, because this is addressing cook stoves with different measures. But if you add up all of the others on top of these cook stoves, you see that for black carbon specifically, we have something like over 60% here, where the overall potential is maybe about 80. So we cover most of what we can do in terms of technical measures, with only a handful of measures and principally 3 sectors that would need to be addressed. And they're pretty well-defined sectors. The measures are also pretty well-defined. They are applied actually in many areas around the world already. And the feedbacks on the other pollutants that are indicated here, like non-methane VOC and NOx, also have implications, of course, for health, contribute to the ozone reduction. And the black carbon, organic carbon, and CO directly are already target of a lot of campaigns and reduction of health impacts from cooking, as well as from transportation. One more slide with implications or reductions of measures, showing the same measures, or selection of them actually, grouped in a bit larger categories. So diesel particulate filters and cooking, heating coal, and heating bio, which is basically pellet stoves. Putting them across different regions, because as I mentioned on one of the first map that I was showing specifically for black carbon, there's different importance of different sources and different future for different sources in different regions of the world. And you see that cooking is, no mysteries here, of course, Africa and Asia. If you look into pellet stoves, the last category, heating bio, we have Northern America and Europe. No really significance of anywhere else in here. Heating coal, the primary target here is East Asia. Diesel, surprisingly maybe to some of you, and originally to us as well, North America and Europe, a fairly small significance. But that is because the assumption is that we do have efficient policies already now in place, that our cars that we are buying now or will be buying soon are actually pretty clean. So that is starting from the assumption that the policies we have in place do work. This is the same picture for methane, just highlighting some of the measures, and I just highlight a few of them, like coal mines, big chunk in here in East Asia. Oil industry distributed a bit more, but it's still Africa, North America, Southwest, Central Asia coming in much stronger. And then agriculture, municipal waste distributed a bit more evenly across. So there is a number of opportunities, and I think this is very important to highlight that there's a lot of things that we do understand about these measures. And that's a big advantage and asset when we talk about these measures. There are several examples of successful implementation of these measures. There is a large potential that has been identified in both developed and developing worlds. These measures do not say that you have to do something only in Asia or Africa. There's plenty that needs to be done in industrial world, in developed world. It's a small number of measures that addresses a very large potential. There's a variety of good reasons, and we are going to hear about them for their implementation. So we don't talk about one particular impact that is targeted. We talk about health, we talk about ecosystems, we talk about climate. We might be even talking about cost efficiency in a number of cases. Several have low cost. In order to find out more about that, I would recommend to look into the UNEP report number 2, the green one that was presented on the first slide. It comes also 2001, 2012. I had a bit more discussion on that. And that's very optimistic, what I'm saying here. But for a number of these measures, we think it is possible, it appears feasible to implement some of them within the 2 decades. So I speak here about very different time frames compared to the cryosphere discussions we had earlier today, although some changes are on the same time scale as well. Now, what is important also to bear in mind, and I'm not specifically asking here for more funding to do work, but there is a lot that we don't know. There's a lot that we can do better, I think, and there's a number of sources we need to understand much better. Flaring, brick kilns, diesel generators, or the wick lamps. So there are some of the sources that we have not yet included. This is a map of flaring areas. This is where associated gas from oil production is flared, and this is an estimate that we made on black carbon emissions from flaring operations. 3 major areas is Middle East, Russia, Africa. There's a lot of other blue, but they are only blue. They are not coming into yellow and red, because while they might have a vast extent, not yet very large, although there are some areas in the US that are growing very fast. Now, what we need to know here is, first of all, we would like people to go out and measure these emissions in a much better way than they are measured now, and understand the strength of that source, and understand how quickly the mitigation can happen. The mitigation does happen already. There's a lot of actions. World Bank is supporting a very good program that we used actually results of to produce that map, tracing what oil industry is doing. So we made in this study a very brave assumption that basically everybody comes down to the levels of, say, Norway in terms of associated gas flaring. A lot of that is simply reinjected or reused if infrastructure is available. This is something that has been highlighted, not exactly in this lot of wiggly lines and complicated map here, but I'll try to only highlight 2 features of this map. This is oil production that is moving more north. That's a projection made by a Norwegian group, actually, in a paper published 2 years ago. This is the 2030 and 2050 map. These black circles around here indicate production areas, oil and gas production areas in the Arctic. This is the Arctic. And if you compare these 2 maps, you see that there's a lot more points, or bigger points, coming here more towards north. Actually, the total volume of production does not increase in this scenario, but it moves much more north. Also, shipping. These are the shipping lines and lanes. See, there's a couple of more connecting lines. Details are not important here. What is important is that there is a fair amount of work that is done on predicting the move towards further north to produce more oil and transport it, get it from production fields to terminals, and get it to our fantastic clean cars with particulate filters. One, nearly the last slide, is about the wick lamps. This is a new study that came out in 2012, at the end of 2012. And that's a chart that shows radiative forcing from emissions only of black carbon emissions from kerosene lamps. This source has been sort of forgotten, or we didn't know. There was no measurement. So these are new measurements that pointed out to the fact that these wick lamps emit pure carbon, basically. And they were, in most of the models that we use and the others, they were classified as sort of cooking fuel rather than lighting fuel. And the difference is much larger than we originally thought. And it might mean somewhere between 3 and 10% increase of total black carbon global burden, but it's really distributed within this area here. So that is something we're working on to include in a systematic framework, and that is a clear candidate for the next measure, an assessment of how important it would be in terms of impacts. So the last slide, a couple of things about challenges. I think we've heard already about some of the challenges in the introduction to this session. Developing technology matching region-specific expectations is extremely challenging. When we talk about cooking stoves, there's a lot of preferences and a long history behind using particular types of stoves in different regions. So it's a big challenge, and there's a lot of activity going out there since decades and not terribly successful. So we are here really on the very optimistic side. Why should we on the pessimistic? That wouldn't be even interesting, I guess, for the perspective from this study. So we think it's doable. We just need to establish mechanisms to introduce them. What we should remember, we have to remember because we have really bad experience with, is that very often a policy that addresses one source has to be associated with a lot of other policies. That is a particular example of diesel regulation that has to come up with low sulfur diesel. And this is one of the reasons that, for example, in Asia, in many countries, we have a delay of about a decade already in introducing further Euro, as we refer to them, lower emission standards for particulate matter, because there is no low sulfur fuel on the market. For many reasons. There's actually really many reasons, and cost is not the only one. Of course, we need the monitoring and understand the progress. Market alone is not likely to drive the change. There's certainly a need for a lot of legislation and additional legislation and incentives. And the last one is about the framework that needs to be identified, and we had an initial discussion of that in one of the UNEP reports, but there's a lot more work that needs to be done to identify framework to introduce these measures. And here I close. Thank you very much.
Thank you, Zige, for the very nice introduction of all these measures that really lead to the application of these measures and the calculations of the impact of these measures. First of all, I want to acknowledge the long list of people that you see here, which compose really the modeling team that participated in this report. And then in this respect, I'm just the voice for the work that all of them have done together. There is some outline of this report, and then I'm glad that Zige has already taken on board some of the messages that I was going through at the beginning, saying what was the starting point of our work, the present work on thin ice. We will look at the benefits for the cryosphere and climate, the health benefit, and also something on crops and the forestry. But there is something I would like to stress before we start, is exactly this concept of the short-lived climate forcers or short-lived climate pollutants, in case this is not familiar to you. They are particularly a group of pollutants of the atmosphere, and in this respect we talk about black carbon and ozone and partially methane, I would say. Ozone and black carbon are belongs to the group of pollutants that they are quite harming the health, but also ozone is also harming the production, agricultural production, and also influencing the forestry. They have a very short lifetime. That's why they are called short-lived climate forcers. We are talking about a few hours up to a few weeks. So it means that although they can be long-range transported, but whatever thing we do at their sources, close to their sources, there is exactly where we have the highest potential of reducing at least the air quality degradation benefits, so the health and the agricultural production benefits and so on. But also we can act on the climate very close to the sources if you reduce that. But as I said, they also are very long-range transport, and they can be transported very long way from the sources, and that's why we have also an impact that they are also important somewhere else. And then we have also methane. Methane has quite a longer lifetime. We are talking about 10, 12 years in the atmosphere. And then, although it's a quite powerful greenhouse gas, it's also a very important gas because it's leading also to the formation of ozone, which then in terms come back to our short-lived climate forcers. So Zig has already mentioned which were the outcome of these two reports, and then I invite you really to go there to look at the reports, the full reports, but also the summary for decision makers. They are there if you wanted to have more knowledge of what was our starting point and which were the things that they were left out from this study. Then we come to the current work, and then we focus on this report mainly on the cryosphere regions. 5 were identified, and we see them in a moment. And then we have more models than they were before, so that the more you run a different type of models, not only you understand the results of your model better through the intercomparison with the other models, but also gives some kind of idea of more robust results. And you are able also to understand a little bit more about the uncertainties related to that. And then what we did here, which was really the huge effort, was to run all these models and evaluating measure by measure benefits that we can see. The actions, Zig already said that they were divided into main groups, the black carbon measures and the methane measures, and I don't want to use the time to explain all of them, but going more in the direction of showing really the model results. So here we are looking at the global map where in the blue we see the identification of the 5 areas where we focus the attention in the report, so the Arctic, the Antarctica, the East Africa, the Himalayas, and the Andes regions. We are looking now the effect on the radiative forcing, which is exactly the impact that these substances have in the atmosphere interacting with the solar radiation that comes in. And then although these numbers do not reflect the same difference in the temperature where you have the radiative forcing, because the evaluation of the temperature is a little bit more complex than then, but gives you already an idea what is the impact of these substances on the radiative balance. And then whenever you see the sign, the minus there, it means that we are going in the direction of limiting the impact on the of the growing of the temperature. So here we are looking at the application of all the measures in blue, and in the red you see the impact on the radiative forcing only applying the black carbon measures. So what you see immediately is that we have a minus everywhere in the globe, which is really good, and then tell us that these measures have a positive impact on the climate. But also we see that the black carbon measures have a strong impact on the radiative forcing compared to the methane one, which you see that doing these differences, it is more or less like minus 0.3 all around the globe. So it is quite uniform. The reason is also because methane has a long lifetime, as I said, and then can travel around the globe much easier than the other one. So that's why the effect is more uniform there. And then you see that the highest impact of all these measures is exactly in the Himalayas region compared to the other one. 2 things must be stressed also from the modeling point of view is that there are 2 regions that they were quite critical to evaluate, taking into account the type of models we had. We are running here just the global models, so they have a quite coarse resolutions. And for the geometry of the South American chain, there is the issue, actually, there is a very long stretch through the vertical, so that the application of the model was a little bit difficult. And also in the East Africa part, where the glacier coverage average is very, very low, but you will see that at the end, the effect of all these measures on the health impact does not leave out any doubt on their impact. We saw also that these measures have a quite different effect depending on the regions where we made these calculations. And first of all, the red arrow that says that remember that we are here to minus 10 watt per square meters, and then we'll see the other regions that is much less. And then what is really obvious that the effect of the cook stove replacement is quite large in the Himalayas. And then while the off and on-road diesel part is really quite important as well. And then if we put in a graph, the colored graph, all the other regions, so here we have actually the ranges down here, and then I remind you that the maximum is -1 here compared to the previous one on the in Himalaya. We see that the cook stove part, the application is still the one giving quite a large impact. And then we can evaluate more or less the effect of all the others. But if you look at the report, you will find really region by region which are the impacts and the reason why we have that. It is interesting to see that also in the Arctic we have the impact of the cook stoves, although the replacement is going to take place quite far away. The air is really traveling quite a lot, carrying this substantial part of the black carbon that is emitted in this Asian country up to the Arctic. So that's why these measures are really so important there as well. And there we have the impact of the off-road diesels on the countries around the Arctic area, as well as the change in the pellet wood stoves, and then also the impact, this is not surprising, of the fires in the Eurasian area. One thing that is important is, I mentioned before when we looked at the plot for the radiative forcing that the methane the change of the methane, the change of the impact of methane applying the different measures was quite uniform around the globe. But this does not translate in the same uniformity in the temperature as well. So here we see exactly the calculations of the temperature change due to the methane measures. And we will see that these temperatures are really, the range is really quite different. And then we see the big impact on the Arctic area. So the temperature change really reflects the type of sensitivity that you have in a certain area instead of another. So it's a more complicated thing than just the calculation of the radiative forcing. And here we see also that the application of the measures have also an impact on the loss of the surface albedo due to the sea ice melting and also the less snow cover. So we are looking at now at the Arctic part, and then the two figures show exactly the change of the application of the two measures for 2050 due to the implementation of all the measures. And then we'll see that the gain of the sea ice surfaces as well as the snow cover both in the summer and the second one in spring. And now let's look a little bit also on the impact on the air quality part, which comprises not only the health impact, but also the ecosystems and the agricultural production. We are looking now at a map, an annual value of the avoided premature mortalities, calculated applying all the measures and evaluating along the globe. So you see very strongly that there are two regions why you have the highest impact, which is a very, very big red dots there on India and China. So the Himalayan areas exactly as the East African areas. So that is quite important. There are two things that we have to say regarding these maps. The first one is that the calculations of the health impact regards the impact of PM2.5 as well as ozone. But the effect on the PM2.5 is much larger than the ozone that ozone has. And the second thing is that the evaluation of this map were done only taking into account the exposure to outdoor pollution. And we know, in fact, that from projects that the impact of people staying in the house is where these cook stoves are really taken is quite important to be taken into account, and actually rises the number by some factors. The most stringent thing I would say is that around 50% of this avoided premature mortality is really due to the cook stove replacement. So that's why this indicates really that is one of the measures that is very, very important, that is taken on board possibly. Then we look also at the effect of the agricultural production. Many, many countries are still actually living on the agriculture, and the presence of high concentrations of ozone are really quite damaging their possibility also to survive. The calculations of all the measures show that there is a very, very consistent and important contributions that we can do in the crop yield all around the globe. So you see here the global production, and particularly all the methane measures combined, plus the on-road and off-road diesels are the measures that are really giving rise to the most benefit. As I said, is ozone the problem for these issues, so that they are the measures that most of all are tackling the ozone concentration. There is something also in the report which is in embryonial phase, but there's still some evaluation of the impact of ozone on the forestry. As I said, is still under development, but is worthwhile mentioning. They are also damaged by the ozone, and then they are also, plants are very, very important things for greenhouse gases. And then the result was that, of course, this was quite species-specific and then a very regional impact on those. As I said, that this is under development, but it is quite interesting to take into consideration. And I wanted to conclude this presentation going back again to the results of the old UNEP reports, because are still valid. On the left part, you see the map of the temperature changes that were evaluated at the time, considering all the measures. So there you see really the impact of all the measures and where these measures are really impacting really with the eye of all the globe. We are talking really about, from the climate point of view, really quite important achievement. But I wanted to conclude with the last graph, which is a quite important graph showing actually the temperature change due to the different scenarios that we looked also partially here and in the UNEP at that time. And then I wanted to especially draw your attention to the line that is the last one, the one in pink. That says that the only way we have to really reach a sustainable future in terms of temperature is really to apply CO2 reduction as well. And this is the message I wanted to take with you when you go away from here. Applying measures for short-lived climate forces is important because these pollutants have a very, very important effect on health and in food availability all around the globe. And then locally, and then in a shorter time frame, they have a quite important effect on the climate. But we need to reduce CO2 as well. We cannot disregard the fact that the more we emit, the more CO2 we stays in the air until we do something. Thank you.
Thank you. And if the Himalayas and Third Pole Group will allow us, I think we'll have some time for questions right now. If that's okay, we can delay by maybe 10, 15 minutes. Okay. And I just, as Director of ICC, I wanted to emphasize really Elisabetta's last comment. Occasionally one will hear people saying, oh, well, this gives us more time to deal with CO2 if we work on these forcers. It doesn't really. You really need to do both. And there has even been some work done by a modeling group at Oxford that says that if you do this and don't do CO2 or do CO2 later, you actually end up worse off than you would have been if you'd never addressed the short-lived climate pollutants at all. So it really is very, very important that we walk and chew gum at the same time, as Americans will sometimes say. In other words, we really have to do both. But these are things that I think, particularly in the World Bank context, it's development, it's going to happen, it needs to happen anyway. The argument is to do it a little bit sooner. And I also want to recommend the full report to you, which we have copies of, or it's available online. There's a tremendous richness to this report. We haven't talked, for example, about the impact on sea level rise, but there is modeling in the report that says that we could perhaps cut the sea level rise that cannot be addressed in any other way because of what's built-in warming from CO2. We could cut it by maybe 30 or 50% in terms of decreasing the amount of sea level rise that is already built into the system. That's important. If you look at that map up there for temperature, although that's based on another report, if you look at Eurasia, the temperature impact follows to a great degree where you have a lot of vulnerable permafrost. And so you might have some benefits to permafrost. And in the appendix, there is country by country listings of the health benefits. And while, you know, the further down you get, the more uncertain you get in terms of the health benefits, still it's very interesting to go in and see what the impacts might be in your specific country from taking these measures based on the modeling. So with that, I'll ask the first question actually that is coming from one of our followers online, and I don't know whether you, Karin, or Zig might be best for this, but one or the other of you, they're asking about what would the measure be if you're going to address wick lanterns, about the potential of solar lanterns or so on. I know the World Bank has some programs and there are others, what those would be to address that if that becomes a source that's looked at.
Well, we can maybe both take it, but it really depends a bit on where it is. I think Elisabetta had that on a slide. It's a bit culture specific. It can be solar in some places. It may be other solutions in others. If you, for instance, can link households more efficiently to a grid, and so on. So I mean, these, as you said, the results are very new on the wick lamps, and we will also start looking into that because, again, there definitely you have an indoor problem. It's because you will use the kerosene lamp inside of the house, and so this is actually a very significant finding in terms of health impacts. But there's not the one solution for all.
So just one word. There's already a couple of options really in use. There's so-called hurricane lamps. There's LED lamps that are already in use as well. Technology, some of the technologies out there, we honestly have not yet explored a strategy that would be a consistent global or regional even strategy. We are at the stage trying to understand fuel use that is very different across regions and type of technology that is already in use, like a share of different types of lamps. This was the first study that made the first estimate. As a matter of fact, Nick Lamb, who was the main author of that study, spent the summer at IIASA, the institute I'm working in Luxembourg, in Austria. And he found out that the results presented in this 2012 paper are probably underestimated for a number of regions. So his new research points to the fact that it's worse than he thought. There's more kerosene that is used in these wick lamps actually than he originally thought. So a new paper might be coming out later this year, coming with updated estimates. This will allow us to think about next steps and also evaluate more critically strategies that could be taken up. Although we are not strategists, I mean, we look at this from the technical perspective, of course, but that's the World Bank that will coming in then possibly with some remedies, together with regional authorities, I guess.
Other questions? Well, if not, we'll go ahead and thank you all and move on to the Himalayas section immediately, and then we'll have coffee after that.
Okay. So we go to the Himalaya section immediately. So without interruption, and then since we are a little late, I ask Dr. Arniko Pandey to start. Thanks. So I ask all the speakers to stay in 20 minutes, and at 17 minutes I will show that only 3 minutes are left.
Maybe here is easy. If you don't mind, I'll just stay here and present from here. So good afternoon. I hope you're all still awake. I'm here to represent ICIMOD. ICIMOD is the International Center for Integrated Mountain Development. It's headquartered in Kathmandu, Nepal, has 8 member countries, basically on and around the Tibetan Plateau, within the countries where the water runs off of the Tibetan Plateau. I'll particularly talk about ICIMOD's new regional program 4 on cryosphere and atmosphere. It's divided into a cryosphere initiative and an atmosphere initiative. Unfortunately, no one from the cryosphere initiative was able to be here today, so I'll present slides that they've passed on to me. There's a fairly large team of glacier researchers at ICIMOD who've been at work for a number of years now. There's a lot of strong reasons for researching the cryosphere in the Himalaya. According to one study, 75% of Himalayan glaciers are retreating. There's a lot of photographic evidence looking at how glaciers have retreated in recent decades. The Imja Glacier here, for example, between the 50s and 2006. As you notice on the bottom there, there's a big glacial lake forming. And one of the concerns in the Himalaya is glacial lake outburst floods. There have been at least 56 recorded in recent times, some of them with huge damage to infrastructure and people. So the cryosphere initiative at ICIMOD, it's based on 3 pillars: on doing in situ measurements on the glaciers, doing modeling work, and using remote sensing and the interactions between them. My colleagues have been setting up field-based mass balance measurements. That's not easy in the Himalaya, where the cryosphere starts at about 5,000 meters and up from there. So it's a challenge always to go to the field sites. In fact, the main work right now is on 2 glaciers, Rikasamba, north of Mount Dhaulagiri, and Yatla Glacier in the Langtang areas of Nepal. There they are on the map, and some statistics about them. And if you look at the picture of Rikasamba Glacier from 1974 to 2010, you notice it's disappearing rapidly. Same with Yatla Glacier. My colleagues have also been starting to set up glacial-hydrological modeling and water resource scenario analysis, and to start to do model runs of the impact of climate change and ice volumes. I'm sharing with you not yet published results from Joe Shea. He used the simplified model of glacier mass balance calibrated with field and remotely sensed observations. And then using sort of RCP 4.5 and 8.5 scenarios with best and worst case scenarios, modeled the glacier mass of all the ice volume of all the glaciers in the Dudkosi Basin area. Found the glaciers are highly sensitive to temperature increases, and that the projected future temperature increases would largely overwhelm any increases in precipitation that might happen with climate change. The ice volume losses he found was between 41 and 60% in 2050, between 78 and 95% in 2100. The Dudkosi Basin, as you might know, is the rivers that run off towards the south from the Mount Everest area. ECMOD over the last year actually got its own MODIS receiving station, has a large remote sensing team that analyzes remote sensing information and get the live data from the MODIS satellites as well as from other satellites. They've been doing glacial mapping, basically identifying and mapping glaciers and watching how they change over time. Some more images from that work. There's a number of publications out of this that were on display outside. I think the neighboring group inhaled most of the display ones as well, but if you didn't get an ECMO pen drive, I have spare ones with all the reports on them as well. The team working with MODIS has also been working on snow cover mapping. Looking at snow cover variations over the last decade and the percent snow cover area, etc. Much of the information from the Cryosphere Initiative is going into building up a regional Cryosphere Knowledge Hub, which is an online resource base with information and data about the cryosphere of the Himalaya region. The Atmosphere Initiative has worked as much newer at ECMOD. ECMOD has traditionally not done a lot of work on atmospheric issues. The initiative itself has only been around since January 2013. I've been at ECMOD since March 2012, building up towards it. And basically trying to address issues of air pollution in the Himalaya and its impacts. There's a current team. We're looking to hire 2 more people. I'll mention more about that at the end. And the objectives of the Atmosphere Initiative are a bit broader than the Cryosphere Initiative. We have a major objective on improving scientific knowledge about emission sources, processes and changes and impacts in the region, but also to study mitigation options that are particularly effective for the Himalaya region, to build capacity, to facilitate transboundary collaboration and sharing, transboundary research cooperation. Air doesn't recognize national boundaries. Scientists shouldn't either, and work together. And to contribute to national, regional, global policy making. I'll kind of show you a bunch of motivating research questions that we're planning to work on over the next 5 years, illustrated with a picture each. For example, what is black carbon's contribution to the melting of Himalayan snow and ice? What fraction of the melting is because of greenhouse gas-induced warming? Because of black carbon warming the air in contact with glaciers, or black carbon deposition onto wide surfaces and therefore melting them, or changes in precipitation amounts because of changes in aerosols. We'll be working on addressing these in collaboration with a lot of other scientists over the next years. On black carbon deposition onto wide surfaces, for example, we're working right now with NASA JPL on a large proposal to have an aircraft fly over the Nepali cryosphere over a multi-year period, measuring light absorbing impurities in snow and ice. Another research question: what's the contribution of the Indo-Gangetic Plains to pollution within Himalayan valleys? I took this picture in January this year. The ridge at the center is the last sort of foothill ridge, and to the right of it is the Indo-Gangetic Plains. To what extent are high-altitude forest fires a source of black carbon for the glaciers? Those fires there are taking place at about 4,000 meters or so, and you see where the smoke is going. By far the highest aerosol optical depth we get in Nepal is in April, when there are a lot of forest fires going on. It's only a short period in the year, but to what extent does the big pulse of black carbon then matter over the course of the year? How do pollutants cross the Himalaya? Since before joining ECMOD, I've had a measurement station in the Kali Gandaki Valley, which is one of the cross-Himalayan valleys with strong up-valley winds. There's quite a bit of haze in that valley. We've been measuring quite high pollution, black carbon concentrations, and it's one of the places where South Asian air can reach the Tibetan Plateau. Meanwhile, south of the Himalayan foothills, there's been a big increase in winter fog. especially over the last 2 decades or so? Is it because of increasing pollution, because increasing cloud condensation nuclei, increasing winter agriculture and irrigation actually providing more water vapor? To what extent is there a feedback with people feeling cold and burning dirty fuels to stay warm and therefore keeping the fog going for weeks? We were planning to do a field campaign this winter. I think we're not going to be ready in time, so we'll do it the following winter, but we'd really like to understand why this has been increasing so much. And to what extent is black carbon actually affecting the monsoon? We hosted a large meeting in Kathmandu in June on changes in atmospheric composition in the Asian monsoon, and there's still a lot of open questions about the extent to which black carbon and other aerosols are affecting monsoon precipitation, and therefore water availability for large numbers of people. Kathmandu is the largest metropolitan area within the Himalaya with a population between 3 and 4 million, has a large air pollution problem, but to what extent is the air pollution problem local, from vehicles, brick kilns, garbage fires within the valley? And to what extent is it actually coming up from the Indo-Gangetic Plains about 50 miles away? We had a field campaign between January and June called SASCAT ABC, Sustainable Atmosphere for the Kathmandu Valley, in collaboration with the Atmospheric Brown Cloud Project. We're still going through analyzing the data, but hopefully we'll be able to answer some of these questions through modeling exercises that follow up. What about the time of day of fires? Look at where the garbage fires are, where the smoke is spreading in this particular picture. Through other work we've been doing in Kathmandu, we found that whether the residence time of air pollution within the urban valley bottom can be anywhere between half an hour to 14 hours, depending on what time of day the same pollution is released. So the time of day of garbage fires, the time of day when rush hour takes place, has a big impact on exposure, even if it doesn't have an impact on overall emissions. So the Atmosphere Initiative EC Mode has a lot of big questions to address. We're a small group. We're trying to build teams and collaborations. We're working on trying to assess the most urgent gaps in the monitoring network across the Himalaya, and to work with partners in a regional monitoring plan that identifies what the priority places are for atmospheric monitoring, irrespective of national borders, but what are the key areas in terms of. To get things jump started, we have some funding to initiate atmospheric observatories in certain locations. And also we'll continue organizing field campaigns. Briefly on observatories, I've mapped here places where I do know black carbon measurements take place, and there's still a lot of gaps. We're working right now with Swedish funding on 2 stations on foothill ridges in Ichakamana, Nepal, and Gedu, Bhutan. I'll show you some pictures. This is the proposed site in Bhutan. In Gedu, we had site visits there multiple times. Here's the view to the south. And then the station in Nepal, in Ichakamana, at a similar height. Again, you can see down onto the plains, and you can see the Himalaya towards the north. It's a wide open peak in a rurally representative area. We're going to have greenhouse gas measurements, aerosol measurements, meteorology. We've submitted detailed reports to the governments of both Bhutan and Nepal and have been answering questions that have come up, but we're very confident that within the next few months we'll be able to start constructing the building while we're already proceeding with purchasing instruments for the sites. So hopefully by the next COP we can actually start reporting data from these sites. We're also working on smaller stations in Lumbini, right on the Nepal-India border, at Langtang, north of Kathmandu, and a permanent station within Kathmandu city as well. Science is not the only part of the Atmosphere Initiative, though. We're also building up work on mitigation, doing a more detailed region-specific assessment of the menu of mitigation choices available, particularly for cook stoves, brick production, transportation, and trying to identify areas to do research where we can add value. For example, in Nepal with cook stoves, the government of Nepal has a plan to replace all traditional biofuel cook stoves within Nepal by the year 2017 with cleaner cook stoves. But they haven't really done an assessment of which ones reduce black carbon the most. What is the best way to go from the cook stoves on the left to the ones on the right? What are good choices? Zig showed a diagram of rocket stoves not really reducing black carbon emissions. We found similar things from some student studies recently. We're planning a sort of a case study in Makwampur district to the southwest of Kathmandu, together with a local medical school and Nepal government's Alternative Energy Promotion Center, where we picked two very similar valleys, geographically, socioeconomically, and we're going to run a controlled experiment where in one of the two valleys we'll replace all cook stoves with the best fan-assisted cook stove we can find. It's about 700 households, while at the same time monitoring indoor and outdoor air pollution in both valleys. And also doing a study of sort of all the social aspects of cook stove distribution, adoption, to what extent do people accept them. We're working with local women's groups with the medical students. We're very close to getting started now with the distribution of the cook stoves, so this is quite exciting. Meanwhile, on capacity building, knowledge distribution, we have seed funds to plan out a new master's and PhD program in atmospheric science focused on the Himalaya, on issues in the mountain regions of the Himalaya. We're looking for senior academics to serve on our international advisory board for that. We've done some and we'll continue to do short training courses as well as distribution materials, films, websites, teaching materials. And we're at the moment urgently looking to hire an aerosol scientist and air quality specialist or engineer. There are details available on the ECMOD website. Meanwhile, on collaborations and contributions to policymaking, as the only international organization focused in mountain areas that has India and China, India and Pakistan, Bangladesh and Pakistan as members, we're kind of in a position where we can bring together scientists to work together that is relatively hard to do without the type of platform we're providing. And so we've been doing gatherings, meetings among scientists, talking about collaborations, talking about things we can do together. We're also in the planning of the first ministerial meeting from our 8 member countries. And since last year, we're an active member of the Climate and Clean Air Coalition. Thank you.
Me to stay here? Or? Yeah. Okay. We'll be good with you. So I now ask Dr. Chichang Kang, and you give 20 minutes as before, and you stay. All right. Thank you. So you come back.
Good afternoon. This is Shichang Kang from Chinese Academy of Sciences. Actually, last slide, I just very briefly and very quickly to go through the two subjects. One is what kind of situations over in the Himalaya and Tibetan Plateau, what's the situation of the glacial change? And the second is how does black carbon at dust speed up the glacial change? So I still keep those two subjects, but today I just for more details. So right here, I said glacial thinning on the Tibetan Plateau and Himalayas, as well as black carbon and dust effects on glacial melt. So this is also two obvious photos comparison in the northern slope of the Mount Everest, it's just like the article showed in other glaciers in the Himalaya. That's obviously during last decades, the thinnings and retreating is very obvious from the photos. Actually, for the national states, not many countries finish all of those glacial inventory. So first you have to know how many glaciers and what kind of different parameters in one country. So China was one of first countries finish the first glacial inventory, and then last year we finished the second inventory. So in that case, you can compare how many glacial changes areas. So we just finished the second inventory, but the point is we not completely finished because those regions always clouds. We cloudified the good remote sensing data. But anyway, compared with the first and second glacial inventory in whole China, we will see those rates are only per year. So just time 10 means 10 years how the glacial areas change. Like right here, if you time 10, so even those regions, 10 years you change like 20% percentage of the glacial areas change. So those in the march of the plateau at Himalaya and also the Tian Shan Altai. But inland plateau, it changes very little. So which means this is from the glacial inventory. And also for the research paper right here, we will see from the area change, mass balance, and also the terminal changes, all retreat, shrinking, and also the length retreat or shrinking. So from these papers, just suggest that strong shrinking in the Himalaya and supplies mass balance or positive mass balance, and less shrinks in the East Pamir, right here, Karakorum. And also weakening monsoon, Indian monsoon and enhanced westerly caused this one. I will explain later very details. So in the IPCC 2007, that was work group 2. They have this report said Himalaya glacier will disappear in 2038. But at the very beginning, when they announced this news for the glaciologists, nobody believed. Because glaciologist only works in a work group 1, not work group 2. So work group 2 just get very wrong information from WWF. WWF also get wrong information from the new scientists. So that's wrong, that continues to make the wrong announcement here in the IPCC work group 2. So at the very beginning, no glaciologists don't understand or agree with this one. So in that case, our German colleagues, he just did the over review of the glacial changes in the Himalaya regions. Right here, you see this dark one is the average of mass balance change, but this yellow one is global average. So which means Himalaya glacial mass balance is decreasing as the same extent as the global levels. So that was not very different, not very strong. It's just like in Chinese we said, you touch the elephant, somebody touches the head, somebody touches the leg. So somebody said, oh, probably Himalaya glaciers it's shrink very fast. Or someone says, oh, it's getting stable. So that's really different. But these papers just did very good reviews for the whole situations in the Himalaya. But in the west bottom, we said here is Karakorum. Karakorum, we have very quite stable terminal changes. So in that case, another research showing that during last 10 years, there was a little bit mass gain, but you see the error bar is very large. So which means in Karakorum, very small regions, you see that the glacier gets stable. Why? Because during last 10 years, the precipitation increased. At the summer temperature increased very obvious. So that was precipitation works very well right here. Of course, here also there was some surging glacier. So that's why they keep stable. Okay. So since all of those regions very difficult to do the logistic for the very remote glaciers, you cannot go glacier one by one. Some researchers just try use remote sensing data. And right here, they said the ISAT data. So even ISAT data for these third pole regions, we will see that negative mass balance during last 10 years is around 0.22 millimeters. That's for these regions. But this research is really funny because he said his result is much less than glacial melt, much less than the station observed. Because station observed, we reach to like the half meters, especially right here. The station are like half meters, but the ISAT data showing only the 22 centimeters. He said because the station always observed the small glaciers, station probably get error. But the point is, if the in-situ observation you are not believe, how could we believe your ISAT data or remote sensing data? So there was lot of controversy. But anyway, those glacial thinning is normal. Everybody agree with this one. But the numbers or the levels is different. Data sources are different. But as we still believe the in-situ observations. And also, somebody used GRACE data. Those GRACE data, but showing in the Tibetan Plateau at the Qilian Mountain right here, it's the best gain during the last 10 years. That's not the truth, because when we observed, later I just show observed. The point is, they just including all of those lake increase, because lake water increased, lake areas expanded. So that's why this GRACE data gets wrong information that thinks this water balance, they think that's the glacial mass balance. So that's wrong things. Because we can calculate how does the water balance, like precipitation minus evaporation, then you get the mass just increased. From the ice core, we also can find the glacial thinning because in the ice core, you have this tritium. Usually it's from the nuclear bombing. Like the 1963, we have already very intensive nuclear bombing in the Soviet Union and other places in Europe. So in that case, in the atmosphere, we have this very high tritium. The elevation concentration is elevated. So after that, it's decreased. But here we have 3 ice cores, just as shown right here. We have those 3 ice cores, but 2 ice cores, like those 2 ice cores, just no any increase, which means those 2 ice cores has lost. Those 2 ice cores have lost the layers in 1960s because 1950s is already increased. So our ice core research just showing, because right here at these layers we have the 5 meters right here, 1963, and then you count the layers going up in 1980s. And also we have different dating techniques showing that for the reference layers, even this we said bismuth for the volcanic. So when the volcanic happens, you have these very high concentrations for the bismuth. So just very quickly going here, we will see. At first, I tell you the elevations. You see right here, elevation in the Himalaya, 6,000. We drilled ice cores in 6,000, but we couldn't find the layers in 1950s. We drilled in 2006, so those glaciers has been melted. And also in Lianqing Tangla, this is in the southern Tibetan Plateau. We also drilled ice cores 2003, but we couldn't find the layers from 1950s. This ice cores is going to the inland of a plateau. We find the layers only up to the 1980s. So which means the elevation close to the 6,000, we couldn't find the mass during last decades. Of course, in the Mount Everest, right here, we drilling ice cores in 6,500 meters, which is really high. We still have the completed records, which means you must remember the different elevations. So for the glacier, we set the ELA. You see, in the accumulation zone, we already lost the mass, which means whole glacier gets thinning. And we have different field stations before Alikon showed Labtuo. Here, this is a very interdisciplinary stations. Not only the cryosphere, also the atmosphere, ecosystem, everything's interdisciplinary. So in these stations, we have one glaciers observed, like those hydrology at glacier surface already built, and mass balance, we use stakes. So for this basin, you see, we already lost 18% of glacier areas. And also the terminal changes, like every year we have 10 meters glacial terminal retreat. You see, I just visit these glaciers for twice. Obviously, the thinnings at the retreat happened. Like mass balance, we have go to the glaciers, set up the stakes to measure the mass balance. Like this mass balances all are negative. From the low elevation to high elevation, all the negative only except 1 year, 2008. So we have accumulated mass balance, and also we have ELA. ELA only 1 year that in the glacier, other year already beyond the glaciers, which means whole glaciers get melt. And for the last 8 years, you see every year we get the thinning of the ice is 1.2 meters. So that's very serious. Here is summary and dramatic thinning of the glacier in the regions and understand, and also the we have to be very cautious about this remote sensing data. Everybody talk about the black carbon, and black carbon have a direct and indirect radioactive forcings. Right here, you see, I just put the light absorbing aerosols, which later on is black carbon, also the dust and some color organic materials. So from here, the first transport, because in the glacier areas, there's low direct emission. So most those aerosols are transported by the long range or transboundary transport. And also, when the deposit in the glacier, we have the light absorbing impurities, and then reduce the albedo, and then reduce the albedo, speed up the glacier melt. But this is feedback. When glacier melt, we have enrichment of all of those impurities or absorbing aerosols. So this positive feedback is very, very important for the glacier melt. You will see usually glacier like this one when the snow covered, but most time when glacier experiences very intensive melting, you see they just get dark. This dark is not only the black carbon, it's also including the dust, very fine particle dust. So we observed this one here because everybody talk about the black carbon. They only use modeling. So right here, we collect black carbon only in the snow pit, not for the whole glaciers. We have very bit data only the snow pit. And also, you see, this is a Flaller. He report the radiative forcings only 3.8, but this research showing we have a radiation forcings even up to 12 or up to 14 watts per meters. So which one you believe? If you don't have any kind of in-situ observation, the modeling can tell you anything, 10 times or anything. So we need the in-situ observation. Well, that's what we did. Like right here, because when you're doing this mass balance and energy balance for the glacial melt, so always they set albedo as a constant, but actually albedo not is a constant. Changes very much, especially black carbon reduced one. So we just visit these glaciers and first we compared the albedo with the mass balance. You see, this mass balance is only 2008. We have a little bit gain in the mass. So our albedo is very high. So mostly there was negative correlations between mass balance and albedo. That's very definitely. So we're going up, collect samples, and also most samples were collected at different elevations. we just measured samples and measured the albedo in situ in the site. Here we have collected lots of samples. I just going down here. So look at why black carbon is important, but dust also important, because during in the foam and ice, because different fresh slope and foam and ice, the dust concentrations is much higher than the black carbon. So of course, we said black carbon is very important, but still dust has very high concentrations, like the 1,000 magnitude higher than the black carbon. We also test this modeling. We said Sticker modeling. Sticker modeling is really good for our observation in this Jadang Glacier. Right here, I report three situations. Like when the glacier experiences the fresh slope, covered by the fresh slope, you will see that black carbon reduct the albedo, which almost like half, like the albedo reduction. Half albedo reduction was caused by the black carbon. This time, the dust is not very important. Others means the particle, the foam size, and foam density, density, other things. This is fresh covered glaciers. But if you see this ice, bare ice, that time the dust works very well, because dust contribute almost 30% albedo reduction. And black carbon is only less than 10. So, which means, but when the ice, when glacier experienced very dark ice, that was glacier really get melt. And if we have aged ice, aged slope, which means the slope is very dark, so still the dust works very like the half. They contributed half for the albedo reduction, and black carbon contributed like the 1/3. This is observation in this right here. But also we can calculate the radiative forcings. You see what's the numbers for the black carbon, dark one. Black carbon in the bare ice, they have 4.5 watts per square meters. But for the dust, it's 33. And also for the fresh slope, number 3, fresh slope, the black carbon has the radiative forcings up to 7. That's really high. So those are the real situation observations. I mean, if any kind of people that doing the large scale modeling can compare with those data. The point is, when I'm saying that these figures show what time the glacier get intensive melt, that was in July. That was in right here, July. So July situation is mostly glacier is bare ice, covered by bare ice. So dust works very well at also black carbon. So if in the July, black carbon and dust get together, we have 30 watts per square meters. So right here, we did the mass balance and energy balance. In 2010, total energy balance is 150, which means dust and black put together, they can work like 1/5. So means this year you melt 1 meter glaciers. If you have this dust and black carbon, you can add 1/5 mass loss. So that's the situation. But for the 2011, it's almost double. So it means this black carbon dust is very important. But point is, in our energy models, never think about the albedo changes caused by the dust and black carbon. So summary, black carbon and dust can accumulated, enriched when the slope and ice melts. And black carbon was a major factor for fresh slope melt, but dust was a dominant factor for glacier melt. So thank you.
Thank you very much. Since the audience seems a little quiescent, it was suggested to have the coffee break now to get some caffeine, come back much more active. So 15 minutes, 3:35, we reconvene.